He's going through the book.
I'll say whatever he say, okay?
Okay.
I'm just recording the book.
Can he hear you?
Oh, shit. I hope not.
Okay. So I have this exam, and let me just start with this exam first.
You turn on the mic.
Can I stop the microphone?
And this is a midterm exam in 2013, and it has 5 problems. The first one is on the relationship between the shear stress and the power and the torque. So the idea here is that once we know the power, which is 400 kilowatts of power, and the RPM, we should be able to determine the torque. And once you know the torque, then you can use the equations for the shear stress and for the twist angle that we've learned in class. So it's a pretty straightforward problem. From the power and the RPM, we can find the torque. And if we know that the maximum shear stress is 120 MPa is a given, it could be given with a, for example, with a safety factor. Once we know that maximum shear stress and the torque, then we should determine the dimensions. The issue here is that if I have a shaft that is not solid, it would have an inner diameter and an outer diameter. So we cannot determine 2 variables for a hollow shaft. So we must know some relationship between the inner diameter and the outer diameter. And that is given in the problem. So the problem, it says that the inside diameter is 60% of the outside diameter. So once we know this relationship and the allowable shear stress and the torque, of course the torque we get it from the power and the RPM, then we should be able to determine the dimensions. And that's the solution here. The horsepower is 400, the RPM is 2000, and then we have the shear modulus is 80 GPa. We make sure that the GPa is 10 to the power 9, and the allowable angle is 15 degrees. We make sure that we convert it to radian, so the twist angle is not to exceed 15 degrees, and we want to find the maximum shaft length. So this number C here, it has to wait until we solve for A, and A is the diameter, B is the stress, C is the length. So first we have to get A, because we have to get the torque is 9.55 times the horsepower in watts here. So you have to convert it to watts, and divided by the RPM. So the torque is 1910 Newton meter. And then we have a relationship between the inner and outer diameter, which is 60%. So you have 1 minus 0.6 to the power 4. That's the kind of the difference between the second moment of area, or the polar moment of area, of the inner minus the outer, or the outer minus the inner diameters. And we know the tau max, therefore we can get the diameter, outer diameter, and from that we get the inner diameter, and we can get the J, and finally the stress. So that's kind of for part A. The length, we know that theta is equal to TL over GJ, so we can reverse this relationship. Once we get the torque, then we can get the length. So to summarize this problem here, the requirement is knowledge of the relationship between the torque and the horsepower and the RPM. So from that knowledge, we get the torque, and then from some level of allowable stress and knowing the torque, we can get the dimensions. And as I mentioned, the trick here is that there's a relationship between the inner and the outer diameter, and therefore we can get the entire dimensions of the shaft. So if you look at this problem, it's not difficult, just a straightforward application on the stress. The second problem that I wanted to review here is an application of beam bending. So it is a stress problem. So the first problem is a stress problem, and the second is also stress. So the stress problem here is, the idea is that we want to combine bending stress with shear stress and with knowledge of Mohr circle to determine the maximum shear stress. And I'm going to explain a little bit more. So in this problem, we have a T section, as you can see here. And the T section is under pure bending. So the bending moment is 10 kip-inch. And at the same time, we have transverse shear force of 100 pound force. So we would expect two types of stresses. One is a bending stress, which is tension or compression, and the other one is a shear stress due to the transverse shear. So this first one is MC over I. So we have to find the moment, we know the moment. So we have to find C, whether C to the top and C to the bottom. And we have to find the moment of inertia, the second moment of area. So MC over I, so the problem is all geometry. So we have to find C and we have to find I. So that's kind of what we need to do. So we will find that and put it on the side. So we got now a tension or a compression stress on the top or the bottom. And then the second part is that we have a transverse shear. So the transverse shear stress is VQ over IB. So the transverse force is V, we know it. Q is a property of the area, so it's another geometry problem, divided by IB, and B is the local width that we would like to evaluate at. And therefore, you have two types of stresses. You have a tension or compression, and then you have a shear. And in order for us to evaluate the maximum shear, we have to combine those in the way that we've learned to find principal stresses or to find the maximum shear. So let me review here now. If we have, first we need to figure out the geometry. The geometry, we have to break it into two rectangles. We have this rectangle and we have this bottom rectangle. And the top rectangle has a C, its own native C right in the center, the 7/8 over 2. And then the second one has its own center right in the middle of this 2.5 inch height. So we can get C1 and C2. We know the two centers. And we know the area A1 and we know the area A2. And therefore we can use the formula that the C top is A1 C1 plus A2 C2 over A1 plus A2. So this is like a weighted mean of the two centers. And now we are kind of using the areas. A1 and A2 are the areas of the rectangles, as you can see here. And C1 and C2 are the centers of their own centers. And then we have to find I1 also for the rectangle, which is BH cubed over 12 for the top. And then the bottom one here would be also BH cubed over 12. Its own native moment of area. And then we have to use to transfer the second moment of area using the parallel axis theorem. And that's what we did here. So we have, we evaluated I1, BH cubed over 12. We evaluated I2, BH cubed over 12. And then we must transfer using the parallel axis theorem And in order for us to do that, we have to find the distances between the centers and the common C. So we have C top minus C1, it gives us D1, and then also have D2. And then we use the parallel axis theorem to have I is equal to I1 plus D1 squared to A1 plus I2 squared to A2. And that's the total second moment of area. And once we're done with that, the problem is solved because we have the sigma on the top is MC over I with a negative because the moment is positive moment. So the top will be under compression and then the bottom will be under tension. We got two stresses here. Next, we go to find the Q. This is the area times, it's the moment of the area times the distance. Gives us the Q, and then the shear stress is VQ over IB. And now what is required is that we wanted to find the principal stresses at the flange, like at these locations. So we could determine, let's say, we want the principal stress at the intersection between the flange and the web, which is like this region here. So we would have to find the tension or compression, and then the shear, which we found, and then we can combine them using Mohr circle to find the principal stresses. So we have sigma 1 and sigma 1 and sigma 2. This is 1, so it should be 2. And that is the center of the Mohr circle, C plus or minus square root of the radius squared, which is tau squared, plus the sigma x minus sigma y over 2. Sigma y here is 0, so we have sigma x only over 2, and therefore we can get the principal stresses. So the summary is that the problem is testing you on your ability to do the geometry, to get the moment of area correctly, and also to use the idea of finding principal stresses or say maximum shear at different locations because you have a combination of two different types of stresses.
So,
okay, next problem is another stress problem, but it's very interesting. And in this problem, we have a shaft that has a diameter d that has uncertainty. And it's a solid shaft that has an outer diameter that the minimum value is 2 inch plus 3 mils. The maximum value is 2 inch plus 6 mils. And we want to insert it into a hollow shaft. And the hollow shaft has an inner diameter of 2 inches minimum and 2 inches plus 2 mils maximum. So there's a uncertainty in the dimensions here. And we want to find the highest and the lowest interfacial pressure and the highest and the lowest tangential and radial stresses. So the problem is the following. We know that there's a basic formula that the pressure, interfacial pressure, is the interference delta divided by the common radius at which you fit the two shafts together, R. And then you have a big factor here that has 1 over the elastic modulus of the outer, and then you have some geometry, our outer square plus the radius square, the interfacial radius square divided by the difference, and then you have Poisson's ratio of the outer, and the same thing for the inner. So this is a formula that you have in the book. So if I have delta and the elastic moduli of the two shafts and the radii is pretty straightforward. I can find the pressure. Once I have the pressure, then I can treat the inner shaft as a cylinder under compression, under external pressure, and the outer shaft as a cylinder under internal pressure. But the problem is that I don't know exactly delta, so I have to figure it out. And here we have minimum and maximum diameters. Therefore, we have to look at the extreme cases. So the extreme cases would be if we take the outer diameter, the largest value of the outer diameter, minus the smallest value of the inner diameter, over 2. Notice that this is over 2 because delta is radial. It's a radial interference. It's not the interference on the diameter. This is on the radius. So we get 3 mils. The worst case is 3 mils. This is the highest interference. The lowest possible interference would be if the outer diameter has only 2.003 and the inner diameter is 2.002. So the outer will be the smallest and the inner will be the largest. And therefore you get a very small interference. So once we know these two values, we can substitute here and get 2 different pressures. One is P high, and that is 18 KSI. This is very standard, 18.69 KSI. And then the lowest is 3.11 KSI. Once we would know now the pressures at the interface, then we treat them as cylinders. And the cylinder, we have an equation for the stresses in a cylinder. If you have an inner pressure and outer pressure on a cylinder, then you can use the corresponding equation. Like, for example, this is the tangential stress is P R, capital R squared times 1 plus R outer squared over capital R squared divided by R outer squared minus the capital R squared. So this is, you have it in the notes, and therefore you can get the largest tangential stress and similarly for the lowest value. So the trick for this problem is just right here, that you have to translate the interference to find the worst case and the best case, and then correspondingly you find the stresses. Last problem in this exam is what I did in class. So if you look at this, you have a step shaft, and the middle is 180 pound-foot per inch. And then we want to find the deflection. So it's a deflection problem. If you look at this, we have to find I1, we have to find I2, and this is symmetric problem, so we split it in half, and then we do only half of the problem. We find the reaction here. So we have a concentrated force, a delta function, and then we have a uniform load starting at 3, and then we make a correction at the intersection. And as we did in class, we make 2 corrections, one for the slope, and the other one is for the magnitude. So that is basically what we have. The moment is 900x minus 90 times the step function at x minus equals 3. So this is step function. And then when we divide by I, then we find this is divided by I1, so everything is by I1. But then we make 2 corrections. One for the magnitude with 0, this is a step, and then one for the slope with power 1. So this is the slope, and then the last term remains the same. And then the integration gives us a C1 and C2, and the boundary conditions is the deflection equals 0 at x equals 0, and the derivative is equal to 0 at in the middle. So this is what I did in class, and it's pretty now you're familiar with it. In one variation of this problem, I put a concentrated force right at the interface here. And then if I put a concentrated force at the interface, the solution becomes very long. And I found out that not too many people were able to finalize a solution on a midterm. The reason is that when I put a concentrated force here, then I break the symmetry of the problem. So it's not symmetric anymore. And then I have to take it from one end to the other. I have to take it from x equals 0 all the way to x equals 16. And then I have to put in the concentrated force. So it would be an additional term in addition to what we did before. So we have to have one correction here, another correction here, because it's going to be 2 steps in the problem. And it turned out to be too long for the solution on the midterm. So I just wanted to alert you that the symmetry makes it easier and manageable, but if I have something additional, maybe a force here, whatever, it could be quite long, but we probably would not do that on the midterm. So are there any questions on this kind of midterm? It gives you kind of a level of understanding of what is required. So you notice this midterm is mostly like stress and then one deflection problem, right? So if I look at the other midterm, this is okay, yeah. The second, this midterm is actually a little bit different. So in here, the first problem is what we did in similar quizzes. So you have a steel that has 18% cold work, and we know the yield, we know the ultimate, and we know the 2 Ramberg-Osgood parameters. The sigma 0 equals 90, and the strain hardening exponent equals 1/4. So the problem is that what is the yield and ultimate before and after the cold work? Of course, before is, we know, 32 and 49.5. After, we expect that this number goes up and this number goes up. So the whole idea is that we know the cold work, then we get 1 over 1 minus W, and that is the strain, and the strain solves the whole problem. So this is A0 over AI, and then when you take the ln of that A0 over AI, you get you the strain, true strain. Once you know the true strain, you use the Ramberg-Osgood relationship, you get the new yield stress, and the ultimate, you get it from conservation of force. The force after is equal to the force before, S ultimate times 1 minus W is equal to S ultimate, and that gives you a little bit of increase on the ultimate. So you take the ratio of the yield to the ultimate before and the yield to the ultimate after, you find that this ratio of the yield to the ultimate increased from 64% to 99%. And when you look at material properties, if the yield becomes close to the ultimate, then that's bad news because the ductility decreases. And therefore, when you plot the stress strain curve before, it should have plenty of ductility, but after, then the yield increases, but the ultimate increases a little bit, and therefore the ductility, which is the failure strain, is reduced. So that problem is from the first part of the course. Another question is qualitative. What is the difference between thermoplastics and thermosets? So thermoplastic softens and can be deformed when it's heated, but is not able to cure. But the thermoset, the material cures, and when it sets, it's an irreversible chemical reaction and prevents reshaping of the plastic. So you have some examples of thermoplastics: polystyrene, polyethylene, and nylon. and thermostats, epoxy resin, polyurethane, and rubber. So these are kind of more qualitative. This is a question that half of it is quantitative, half is qualitative from the information we have in the first part of the class. Second problem is a beam that has a uniform load and transverse force. So this is a 3D problem, but it's very simple because we have two planes, the X, Y plane, and we have the Z, X plane, and then we do pretty much two different problems. One is in the XY and one in the XZ, but both of the two problems are simple by themselves. So this is, I'm not going to go over that because it's pretty straightforward here. Just to alert you to what we would have. Next problem is a problem of deflection. And the deflection problem, we have a beam. It has a uniform load, and it has a simple support at point A, and then another one at point O. And then we want to find the deflection. So this is a nice one because we have uniform load, we have a concentrated load of 1200 from the reactions, another one of 400, and therefore we can use the singularity functions to write the Q equation and then integrate it, find the moment equation, and then integrate it again twice to find the deflection. First, we get the moment, find the Q is basically R0, x to the minus 1, because it's a delta function. RA is positive, x minus 8 to the minus 1. And then we have a uniform load, starts at 8. So it's W, which we know, times x minus 8 to the 0. And then we have to terminate it at the end by taking plus W times x minus 16 to the 0. So these two step functions, one starts, one ends the distribution. And then we integrated once to get V, integrated twice to get M, no constants in this integration. Now when we do the deflection, we take M equals EI times the second derivative, and then we integrate once and twice, then we have two constants in the integration. So we have C1x plus C2, and then we determine C1x and C2. Now the trick for this is that the displacement here at O is equal to 0, and also at 8 is equal to 0. So it's kind of a little bit different. You have one displacement here is 0, one is 0 here, instead of at the end, because at the end is going to deflect. And when we put these two conditions, we can find the C1 and the C2 and determine the maximum deflection. It says, determine the maximum deflection. So by common sense, well, if we just have C1 and C2, we can take the derivative, find out where the maximum deflection. But if you look at it common sense, the beam is gonna bend this way and then go to 0, and then is going to maybe go up and then down again. So deflection maximum could be here, or it could be at the end. So you have to test it maybe at the end here first. Instead of taking derivatives, you get it at the end, and then you can get it in the middle right here or close to the middle. But in this case, at the end, it turned out to be the maximum deflection. So that's kind of a deflection problem that we have. Another problem here is a torsion problem, and the torsion problem has a thin wall, and the thin wall has a fillet, and the fillet radius Ri. And we wanted to compare the shear stress when Ri is equal to 0 or Ri is equal to 1/4. So two different cases. So when we do the torsion problem, we have to use the torsion equations that we for thin walls in this case. So it's a thin wall solution and for torsion. And if you go back to your stress section, stress examples, you find that we have what's called Brett's formula. So Brett's formula give you the shear stress in thin walls, knowing the mean perimeter. So if we have to calculate the mean perimeter of the section, and then knowing the thickness. So the mean area, a mean, is we have to draw a line which goes in the middle of the section, which is 1 inch minus the t over 2. This is thickness over 2 squared. And then the mean median line has a perimeter, is 4 times the size, because we have 4 sides. And then this is Brett's formula here. Torque is equal to 2 times the mean area times thickness times tau, the shear stress. And if we know tau, as for example, is given as a limit, then we can find the maximum limiting torque, and vice versa. So we can have, these combinations of parameters in the solution. Now, when we have the fillets, then the geometry becomes another geometry problem, because I have to find basically what is the mean radius, the median line. We have the radius at the median line, and then we have to find now the mean area. So it becomes a little bit of geometry problem, because you have to subtract. So what you have to do is you have to get the area of a square, and then you subtract all of these quarter circles from the sides, because each circle here is just gonna take away from the sides. And so that's basically what it is that we get for the second part, for the second part, it has more geometry calculations, like 4 times, like for example, the area this is the area of the square, and then you subtract 4 times the corners, and then you have the quarter circles in here. Then you just have to do this calculation. So the mean area, same thing for the mean median line here. Okay, so this problem, if I summarize it, it's a thin wall problem, Brett's formula, but the difference is that when we get these corners, we do some more geometry work on it. Last problem that I'm going to review is Castellanos problem. And here we have a link, and the link has a support here, the simple support, and is supported with a quarter of a circle, another link. So it's hinged at C, hinged at A, hinged at O. So we don't have any clamp support in there. So since it is hinge here, hinge here, hinge here, then we would expect that we have a totally determinate problem. But we just have to do it carefully. So if I have, we have to do free body diagram. So I have to take this OB link and put forces here, put the forces here, put the forces here, and then do equilibrium. And then I have to take this link here, the quarter circle link, and do a free body diagram. And then when I combine the 2 free body diagrams, I should get total equilibrium. So if you look at, this is the initial structure. Then we have the force is at B. So the force, the external force is at B. So if I take the 2 together, so I'm not going to separate them at A. If I take the 2 together, then you have a force at A, you have a reaction at O, and a reaction at C. But since I don't know if the reactions are horizontal or vertical, then I have to put both vertical reaction and horizontal reactions. And in fact, I do, if I take vertical reactions, then this would be 2F and this would be 3F to balance the F from the moment equilibrium and vertical equilibrium. But if I take moments now about let's say C, then I must have a horizontal force 3F here, and therefore this has to be 3F. In other words, if you put the two links together, you conclude that at C you have two equal forces, one vertical, one horizontal, and at O you have two forces that are not equal. You have 2F and 3F in here. So once we have this, then we could do we can get the deflection at B, like we need the deflection, let's say at B here, the vertical deflection. So we have to calculate now all of the energies for axial and for bending, and then find the deflection by using Castellanos theorem. For the axial is FL over AE, dF by dF over A by dF, which is what we have here. So the derivative gives us 3. And then this second part is the bending for the straight section from 0 to 12, which is this straight section here. It has an energy stored. And then we're going to have to do this section also. And then we have to do the energy in this section. So we have 1, 2, 3, plus the axial part. So the axial, we did the axial. Then we have to do the 2 bending for the straight sections, and then the bending for the curved section. When we do the curved section, then you get these cosine and sine. And as I mentioned in class, you get sine squared, sine cosine. So this is a kind of a little bit more trig problem once you have curved sections. So once you have these curved sections, you gotta go do some trig. And then, you know, in the exam, we're given that the integration of sine squared d theta from 0 to pi over 2 is the same as cosine squared, pi over 4, and sine cosine is equal to half. So all of this is given in anticipation that you'll be able to figure out the moment in a curved section and take its derivative with respect to the angle on the curved section. So that's basically, I reviewed a wide variety of problems for the midterms, and I think this kind of representative. So, you know, we would expect something very similar to these types of problems. Are there any questions? Okay, so I think I'm gonna stop at this point, and then I'll just make the recording available online just in case people would like to watch some more. Okay, so we'll see you later. Okay, thank you.